Accelerated generative models for point cloud data. Point clouds are quickly becoming the de facto data type for many applications related to 3D perception. This is in part due to the proliferation of low-cost and highly accurate 3D range sensors, as well as the rising interest in areas such as autonomous driving and augmented reality. It is therefore important to know how best to utilize point cloud data for these 3D perception tasks, and thus explore different types of representations for point cloud data that may help facilitate or accelerate their common underlying operations. Due to the large amount of data produced by modern 3D range sensors, most applications typically discretize the data in the form of voxel grids or octrees. But our work takes an approach of statistical parameterization through generative modeling. To do this, we reinterpret the points as an IID sampling from some unknown probability distribution, and then optimize for those distribution parameters. If the PDF accurately reflects the statistics of the original point cloud data, we can then discard the raw points and work only with the PDF, which may need only a relatively small set of parameters to be useful. Furthermore, being probabilistic, we can utilize the same optimization for principal denoising and outlier handling. Though other generative techniques exist, notably for point cloud registration, we propose a novel top-down hierarchical variant that exponentially speeds up construction relative to the size of the model, and is also particularly well suited for parallel architectures such as the GPU. To create the model, we first perform a coarse compact segmentation into Gaussian mixtures using a point parallel modification of the EM algorithm. We then recurse this process at each individual mixture, producing more coarse models at finer and finer spatial granularity, such that when combined together again produce a very high fidelity global model. The process is similar in spirit to the creation of an octree or KD tree, where recursive spatial subdivisions are made in order to compress empty space. In our case, however, we do not use voxels, but instead use probabilistic Gaussian kernels. And in contrast to an octree that places points by repeated coordinate comparisons, we perform many small-scale maximum data likelihood calculations to place and reform the mixtures in order to better capture the underlying statistics and geometry of the original point cloud data. Our proposed algorithm therefore produces a Gaussian mixture tree where different levels of the tree can be regrouped to produce different levels of model fidelity. Thus, each model has a different fidelity to size trade-off that may be leveraged at runtime according to different application-specific demands regarding available bandwidth, memory, or computational resources. We can show the compactness fidelity trade-off visually by producing a heat map PDF representation of the model at different levels. Note that for even high fidelity models, our data footprint is much smaller than the original point cloud size. Additionally, the generative structure allows for statistical point cloud resampling. One can see how resampling from different layers of the tree produce greater and greater fidelity until 4 levels of recursion produce a visually indistinguishable point cloud from the original data. We can also use this resampling technique in order to visually compare other probabilistic generative models for representing point cloud data. Here we have a scene of a lounge taken with a Kinect. By taking samples from similar generative models, we can clearly see that our proposed model does a much better job at faithfully recreating the geometry of the scene. The parameterization can be used directly in many applications that require quick spatial probability estimates. Here we use a Monte Carlo resampling technique to quickly create an occupancy grid of the same lounge scene. Our proposed technique, deployed as a top-down hierarchical approach on the GPU, confers benefits of speed, size, and fidelity over other generative techniques. In general, we see many benefits to using a generative approach for point cloud modeling over voxel-based approaches due to their statistical nature and compact size. Thank you.